Good morning, everybody, and welcome to today's webinar. I'd say just good morning, but it looks like we have a full domestic and international audience today, so good day to everybody. I do appreciate you taking time here today to go over this information with us. Today's topic is going to be review of a safe workstation for electrical safety testing. If you've attended some of our previous webinars in the year, you will see a repeat of some of this information, but this one is geared specifically towards the work testing station. And we feel this is a very important topic. We do this one every year in some way, shape, or form because obviously safety is one of the most important things, if not the most important thing to deal with when we're talking about electrical safety testing. So that being said, let's get into it. Before we get full on into the presentation, we want to cover a couple things with regards to the GoToMeeting itself. There's a couple utilities you're going to notice on the right-hand side for your GoToMeeting toolbar, and that is primarily the chat and Q&A. If you have any problems with the running of the presentation or the meeting itself, as in my audio is cutting out, there seems to be a lag in the video, something along those lines, let Jim know. Jim is our host, and he can help you out with that, so address those to Jim Kennedy, and we should be able to sort you out in short order. If you have any questions relating to the material itself, go ahead and address those to Syed. Syed Abidi is our applications engineer. He's very knowledgeable on these topics, and he is here to help answer any questions you might have during the webinar. If there are questions that we feel may benefit the group to hear, we'll save those for the end, and we will have Syed or Jim ask those questions at the end, and then I can address them. Every time we do one of these webinars, there is a question that is just too in-depth to be answered in a short period of time that we have for the Q&A session at the end. So if that does happen, you can always feel free to contact us directly to ask those questions. We'd be more than happy to help, walk you through an application, answer any questions you might have regarding the material or just electrical safety testing in general. We've been doing this for a long time, and we like to help people out. So we will give some more contact information at the very end of the webinar. This webinar is being recorded, and it'll be available to view within a couple days on our website in the webinar archive. If you want a copy of the presentation slides themselves, email Jim, which is jimk@asresearch.com, and he'll be able to send that over to you. So that being said, let's get into it. Now, I'm assuming we're going to have quite a bit of a different crowd than we did last time, but just a quick recap in case you are curious to go to our archive and check out what else we've done. Last time we did a Touch Current Testing 101 and 102 series, and the one we did earlier this month was the Touch Current Testing 102. We got pretty in-depth with leakage current testing. It was more specific towards the medical field, but we talked about touch current, patient testing, patient auxiliary, and mains on applied part leakage testing. We talked about how leakage is measured, and then we related all that to the 60601 3rd edition standard, what leakage current tests are run and what that all means, and then we went through some testing examples as well. I also did a few video examples on exactly how you can run these types of tests. So if that's something that interests you, go back, take a look at our webinar archive, and you'll be able to play that back. But today, we are covering quite a bit of a different topic, and today is all about safety and building safeguards into your station. I anticipate this webinar to take anywhere from about 40 to 45 minutes. I like to leave some time open at the end for questions, should we get any. Our last webinar ran a little bit long, but it was a pretty complex topic. I know people have things to do, so I like to keep it short, sweet, cover a lot of important information, but cut out the fluff. So that being said, what we're going to cover here today with regards to the safe workstation is, first of all, I'm going to give just a brief introduction to safety, and then electrical shock hazards, how they happen, what it can mean, and what its effects are on people. Then we're going to get into the operator themselves. If you're using a piece of electrical safety testing equipment, there are certain things that you really should know to be qualified to operate that equipment. So I'm going to go over 10 things that a qualified operator should know and be aware of when they're using this type of equipment. And if you know those things, I would consider that you are a qualified operator to use this equipment. Then we're going to go into a little more detail about building additional safeguards in. We do understand that every station is different. Not everybody can have all means of protection in a station, especially if we're talking about a very busy automated environment. So we go over a couple different examples of what you could do to protect your operators, and then we go over some additional safety methods, some additional means of safe testing. Nice thing there is it gives you some options. So if you can't go route A, maybe you could go route B, C, or D to have a safe station. Even though it might not have all the elements that you would ideally want for a workstation, there's still a lot you can do, and there's a lot of flexibility with regards to setting up your station. And then at the very end, I want to go over some training resources, stuff that we have available, and information you might find very helpful, especially if you're new to this and you're trying to set up a safe workstation. Some of the resources that I'm going to point out to you guys should be really helpful in that regard. So that being said, let's get into it. So what is safety? I mean, just the general definition of safety is the condition of being safe from undergoing or causing hurt, injury, or loss. Pretty basic, pretty self-explanatory, keeping somebody safe. In the regard of product safety, what we're talking about, and this is really what we're going to be talking about here today, but also keeping the general rule in mind, is a device or a machine designed to prevent inadvertent or hazardous operation. I'd even go further as to say, with what we're going to be talking about, it's not just a device or a machine, it's really a system. It's a system that you have in place to prevent a hazardous operation, and a truly good safety system almost takes the thought process out of it. And not that you want to not be thinking about how to be safe, but almost to the degree that there's almost no way that somebody could get hurt when using such a system, because it's so well designed that it's almost automatic in how it prevents some type of hazard. So I think really to understand safety, it's also really important to understand what can happen when something does go wrong. And this kind of relates to why do we test in the first place? Why do we run these high pot tests or dielectric withstand tests or leakage current tests, earth protective conductor tests? Why are we doing these in the first place? And I think there's really four main reasons. Obviously, you could probably say there's 100, but if you break it down into the core reasons, what we're really dealing with here is safety, quality, cost control, and liability. For safety, we want to ensure that the product isn't going to pose a hazard to the end user. That's why we run these tests, and that's why they're called safety standards. For example, IEC/UL 61010-1 3rd edition for laboratory equipment. It's a safety standard. It goes through all the different hazards that a product could pose, how you mitigate those risks, and how you test to make sure that it's compliant with those standards. There's a reason we have standards. It's to make sure that everybody's on the same page with regards to testing and compliance, so that we make sure that the products out on the marketplace are safe for use. That also plays into quality. We want to be able to detect defects, prevent faulty components from being installed. If you have a high degree of quality, there's a good chance that it's also very safe, and that plays a part in the standards as well. Cost control. We want to identify problems before they're shipped, because if you don't, and you do find out that there is an issue, you're going to have to recall that product, which can be very costly. We've probably read user reports, and you've probably read online about companies having to recall products, and a very large company having to recall a specific line of products can cost in the millions, if not tens of millions of dollars. So there can be a lot of pain and suffering saved on the back end by simply going through and taking the time up front. Liability, preventing suits. It's the responsibility of all manufacturers to run these electrical safety tests. If you're manufacturing an electronic product, there's a very good chance that you have to be running these electrical safety tests, at the very least in the laboratory, like what we call a type test, and in most cases there are several production line tests as well. A lot of what I'm talking about here today, but not all, does relate to a production line because we're talking about fast throughput, and I think when you deal with a scenario where you have a lot of operations going on at once, it leaves it open to somebody not paying attention and then that's when people get hurt. In laboratory environments, it certainly applies as well. I'm not trying to say that's not important, but laboratory environments, it tends to be lower volume. People tend to be more cognizant of what's going on in the immediate area and know what they're doing and how to use the equipment, whereas on a production line, there's a lot going on. There can be distractions, things of this nature, so there's a lot of safeguards you can build in to make sure that type of thing doesn't happen. Let's look at some potential shock hazards. And they come in several different variations, but these are the main ones that we tend to run into. So on the left-hand side there, you can see Abraham Lincoln is touching something that's energized, obviously, and he has basically contact made with one point of a circuit, while Abraham Lincoln is at ground potential. So what's happening is he's touching a hot point, and the current is flowing through his arm, down his body, and into the ground. Because the current has found an attractive path through him. One thing you have to realize, if you don't already, is that electricity it's lazy. Current is very lazy. It's going to take the path of least resistance. And if that path is you, it's going to take it. It doesn't have a consideration that you might get hurt or not. But you don't necessarily have to be touching an energized circuit. You could touch a hot metallic part while you're at a ground potential and cause the same type of hazard. Let's say that internally on a product, let's say that you have a product that has a big metal chassis and a line cord or a cord that's running line voltage has frayed insulation, and that now has exposed conductor, and that's touching the metal chassis. Well, current is going to now be flowing through the chassis as well, and if you go touch that and you're an attractive path for the current, it's going to go through you. But you don't necessarily have to be at a ground potential for that to be the case. As you can see on the right-hand side there, that's contact made with two hot points of a circuit or 2 points of a circuit. Even if you're not at ground potential, if from hand to hand is lower resistance than the path the current was going to take through the device, it's going to go through you. And that's pretty much one of the worst case scenarios, because what you have there is hand-to-hand contact. That means current's going through your chest cavity, which is bad news. So those are just some potential hazards you could be dealing with here. And my point on this and the takeaway is that current is going to go anywhere it can find a low resistance path, whether that be you or a circuit or whatever the case is. So we really want to make sure that we mitigate contact with such circuits, and there's ways to do that. Now, as far as the severity of electrical shock, that really does vary. There's no set rule that governs this. It really depends upon several factors when we're talking about if somebody comes into contact and they do get shocked. It depends on your physical condition and your response time, the path the electrical current takes through the body. As I just explained, it's worse that if you're going across your chest cavity than, let's say, going through your arm and out your leg on the right-hand side of your body, or even, through one part of your arm and out the other part of your arm, which might be very uncomfortable. You might get a shock or something along those lines, but you'll probably be okay. The duration or length of time a person is exposed. Obviously, the longer you're exposed, the worse it's going to be as the electricity goes through your body. The magnitude of the voltage and the current flow, and we're going to be actually delving into that a little bit more heavily in a couple minutes. And then the frequency of the supply voltage. Frequency actually plays a really big part, especially when it comes to cardiac arrest. For whatever reason, I'm not a doctor, so I don't fully understand the reasons for this, but I do know that in the 40 to about 100, 120 hertz range, it's a really bad range of frequency for you to get hit because it can cause fibrillation in the heart. So standard line voltage coming out of the wall in the United States is 60 hertz. In Europe, it's 50 hertz. It falls into that range. You do not want to get hit by wall voltage. It falls into that range, and it can be quite dangerous if you were to get hit by something like that. It can also depend on whether you're a man or a woman. Men and women have very different physical responses because of body composition. We're a little different, the way our bodies are composed, and so the severity of the electric shock can vary based on whether you're a man or a woman as well. Now, if we're talking about the effects of current on the human body, I do have a general table here. Again, this can vary depending on various factors, what kind of environment you're in, what kind of conditions that you're in, kind of what I explained in the previous slide. One thing to keep in mind too, these effects that I list right here are for voltages less than about 600 volts. Now, many electrical safety testers can output in excess of 5,000 volts. which causes much more severe reactions at lower current levels than I have listed here. So I would definitely take that into account when you're considering, when you're using an electrical safety tester. You might definitely feel something below that perception level that I have listed here if you're dealing with 5,000 volts as opposed to 500 volts. The 600 volt mark, right about 6 to 800 volts is actually the breakdown voltage of human skin. And human skin does provide insulation. It's a barrier. It is an insulator. But it does have a breakdown voltage like any other insulation. And if that happens, that's when there's trouble. So if we're talking about current from the 500 microamp or 0.5 to 1 milliamp range, that's the perception level. That's really where you're going to feel like a slight tingle. It's probably not going to hurt. It'll feel a little bit uncomfortable. And most of you have probably felt something like this before on a piece of equipment. There's a slight tingle felt, maybe a little shock, a static shock or something like that. Very small amounts of current, but that's when you're feeling it. When you jump up to about the 3.5 to maybe 5 milliamp mark, this is when you're going to feel a slight shock and you're going to have a startled reaction. If you ever accidentally, let's say you were plugging something in and maybe you had the tip of your finger close to one of the blades on the plug when you plugged it in and you got a little jolt, you probably were right in about that range. I know I've done that before accidentally. Doesn't feel good. You do get that startled reaction and you jolt right away. While this may not pose a shock hazard or a severe shock hazard, you still get a startled reaction, and in many cases that doesn't matter aside from the fact that you get a little jolted. You might be a little scared by that, but if you're in an environment where there's a lot of moving parts, or maybe you're up on a ladder or something like that, a startled reaction can actually be a pretty bad scenario. You don't want to obviously get startled and fall off a ladder, or get startled and accidentally wind up putting a hand or something like that in a moving part, which, I read reports on this kind of stuff all the time, and that happens. They were dealing with a relatively low current level, but when they got hit, the startled reaction caused a movement that then caused a mechanical injury. When we move up to the next tier is really when we're getting into trouble here. In the 6 to about 30 milliamp range, and again, that varies for men and women. The threshold is actually slightly lower for women than it is for men. That's when you have a painful shock, and you could have the inability to let go, muscle contraction, to where you actually cannot let go of the circuit. And that really is bad news, because the longer you're exposed, the worse it's going to be. The worse the damage, the better the chance that you're going to go into cardiac arrest. When we jump past the 30 milliamp mark is what I call the red zone. Really, the tier before it is kind of red zone as well, but this 30 to 150 milliamp mark is extremely painful. This is where you can go into respiratory arrest, ventricular fibrillation, and death is certainly possible. It's possible at the lower levels as well, depending on your condition, but most often when we're talking about death from shock, we're talking about this range and above. And then, of course, anything above 150 milliamps, I know this table jumps to 10, which is a huge amount of current. That's cardiac arrest, severe third-degree burns, and most certainly could be fatal. So something to keep in mind as we move through this material. Now, when we're talking about human body resistance, it has an average of 1,000 to 1,500 ohms of resistance to the flow of electrical current. That's a pretty conservative estimate, and by conservative I mean that's low as compared to if you were actually to measure it. But it's better to think in these terms. You want to assume that it's going to be 1,000 to 1,500 ohms, because the lower that resistance, the more current that's going to be able to flow through your body, the more attractive that you are going to look as a path for the current. Now, the outer layer of our skin, as I was talking about before with the breakdown voltage of skin, is the largest percentage of the body's electrical resistance. Once that's punctured or breaks down because of voltage or current or whatever the case is, it ceases to act like a resistor, and then that only leaves body tissue, nerves, things like that to impede the flow of electrical current. And unfortunately for us human beings, those things don't impede the flow of electrical current. They're actually pretty good conductors. I mean, if you think about it, your nerves communicate with electrical signals, so they have to be decent conductors. But unfortunately for us, once the skin is punctured, you really don't have much of a safeguard against the electrical current. Because of those blood vessels and those nerves. So if we look at a couple examples of some models, let's say, of different contact points, I said 1,000 to 1,500 ohms. Now let's just assume 1,000 ohms. And 1,000 to 1,500 ohms assumes a very large contact area. So if you look at the Abe Lincoln up in the upper left-hand corner there, what that's representing is full-on hand-to-hand contact. Like if I were to take both of my hands and wrap them around a conductor like the size of a Coke can in each hand, that's a lot of contact area. That's really when you're talking about this 1,000 to 1,500 ohm range. If you were to actually measure that out, it may even really be more than that. But again, I like these conservative estimates. Now, let's just say you were to contact a line voltage at 240 volts with 1,000 ohms of resistance. That gives you 0.240 amps, which is 240 milliamps of current. Jumping back, 240 milliamps is in that death possible range. That's even above the 150 milliamp mark that you see right there. So it doesn't take a whole heck of a lot to get into a really bad scenario. Now, even if you bump that up to 1,100 ohms, let's say it's not going from arm to arm, but going arm through down to the grounded boot that Abe Lincoln's got on there, and you're still talking 218 milliamps. Still a lot of current. Now, if you were to go ahead and look at the top right-hand Abe Lincoln there, now we're talking fingertip to fingertip contact rather than whole hand. And a little bit better for Abe there, because now we're talking about 20,000 ohms of resistance. So you see that resistance went up by like a factor of 10 by simply changing the contact area there. So now we're talking about 12 milliamps, in which case, if you looked at the chart, Abe might get a startled reaction. He might jerk back, and he may or may not be able to let go, but at least he's got more of a chance than the 200 milliamp mark. I actually did a couple of experiments where I took a multimeter and I held them in my fingertips to see what kind of body resistance I was dealing with. It was actually closer to about 120,000 ohms, and I even wet my fingers. I got my fingers wet, and then I held the leads, and it was like in the 100,000 ohm range. So it can be quite a bit higher. Dry, it was like 600,000 ohms. So your skin does actually act as a pretty good insulator, but when you're thinking in terms of safety, keep the low numbers in mind, because if you get that base covered, you'll be in good shape. So now that we've been talking about all these shock hazards and I've sufficiently scared everybody with Abraham Lincoln diagrams, we wanted to ask you guys a quick question about your electrical safety testing setup, if you are currently using one. If not, I think this information will be helpful, especially if you're looking to move in that direction. But how confident are you guys that your safe testing station is sufficient to protect your operators? Does it leave it open to where somebody could contact a live energized circuit? These are really things to think about. So we did want to ask you guys this. Let's take, let's say 30 to 40 seconds or so to answer this question, because we want to get a feel for what you guys are thinking.
Hey Nick, it looks like the results we're looking at 12% were extremely confident, 32% were very confident, 40% was confident, 12% not so much, and 2% not at all. So I'll turn it back over to you, and thanks everyone for participating.
Yeah, thank you guys for answering those poll questions. That really does give us some really useful information, and I was hoping that not every 100 wasn't going to get 100% very confident or extremely confident, because then it's like, well, why are you attending this webinar? Maybe a gut check, I don't know. But that's an interesting distribution, and some very honest answers there. And again, that's why I'm really happy that you guys are attending this webinar. We're hoping, that's why we give these things out for free. We're hoping this information is useful and that you can use it within your own training documents. email Jim and ask him for the presentation. We have no problem giving this information out. If you have other questions, after the webinar, call us up. We'll discuss your setup with you. We even do on-site training. We'll come out and we'll look at your setup and give you recommendations, say what you need to do. So these are all options for you guys. We want people to be safe when they're using this type of equipment, whether it's ours or competitors. Hopefully it's ours, but even if it's other people's, we want you guys to stay safe. So that being said, we talked a lot about hazards, all that good stuff. So let's really get into some more meat and potatoes of this presentation and talk about the qualified test operators. Here's 10 things that you guys should know if you're using this equipment, whether it's on a regular basis or not. Even if you're just using it once a week, once a month, these are things you should know to use this equipment at all. That's one thing I really want to remind everybody of. It is safety testing equipment. It outputs high voltage. It can be dangerous if used improperly, even with the safety checks in place. All of our instruments have safety checks built into it, but things can still happen. So, first one, determine if an exposed conductor is energized. If I was running a high pot test on a DUT, when I say DUT, I mean device under test. If I was running a high pot test on a DUT, how would I know? Is the test running? Is it not running? The example that I'm showing there is you'll see on, this is our Omnia 2 series multi-test instrument. We have these caution high voltage signs on the front of it that will actually flash red when the output is active. So on our instruments, it's actually pretty easy to tell when the high pot tester is active because you see front panel of every single unit, that caution and both of those symbols are going to light up and flash red. Number 2, determine the nominal voltage of an electrical circuit by reading drawings, signs, and labels. Know how to use the equipment. I know they're not the most fun things to read, and I know this because I write them, but the product manual, the quick start guides, every single one of our units, and almost every unit, competitor or otherwise I've seen, it's going to come with a product manual and a quick start guide to let you know how to use this thing. Look at a label, like I show an example of a cord there that shows different warnings and ratings and things like that. Know where to get that information. Even if you don't know it off the top of your head, which most people don't. I mean, I don't know on a lot of pieces of equipment right off the top of my head where it's located, but I know where to find it. And if you know where to find it and you can reference it, that's really the important thing. For example, as you can see there in number 1, electrical circuits, diagrams, whatever, it's showing you caution. Hey, look, this thing can output 5 kV AC and 6 kV DC. That's an indicator right there of the level of shock hazard you're dealing with. Right on the front panel, you're able to determine that. But again, look at the product manual, read the product manual, and look at the quick start guides. Our product manuals actually have a lot of safety information in them and warnings and hazards about what you really need to be doing with these setups. So it's good to be able to look through those things and determine the types of hazards you might be dealing with. Know how to use that equipment before you ever use it. At the very least, read the quick start guide because it gives you simple explanations, and it won't take you more than about a half hour to go through all of that, set up an instrument, and be ready to go. All right, so delving into the next round, let's look at the next few. Understand approach distances and corresponding voltages. What I mean by approach distances is from NFPA, the National Fire Protection Agency, and the NEC, the National Electrical Code. Safety approach distances are basically how close can you get to that circuit, and it really depends on voltage level as well. And with regards to approach distances, for anything between, I want to say, 750 and 15,000 volts, the prohibited approach boundary is 2 feet 2 inches. What that means is, even if you're a qualified operator, if you get within 2 feet 2 inches of that energized circuit in the 750 to 15,000 volt range, you have to be wearing personal protective equipment in the guise of high voltage gloves, whatever the case might be. If you don't have personal protective equipment, even if you're a qualified operator, you cannot get within 2 feet 2 inches of that energized circuit. And obviously that's for safety reasons. Stuff can arc over. Air like anything we've been discussing here, air is an insulator, but it has a breakdown voltage. And when you're dealing with 15,000, 20,000 volts, stuff can arc through the air right over to somebody's hand or whatever the case might be. I've seen it happen. So that's why even if you're qualified, you're not supposed to get within these boundary limits unless you're wearing personal protective equipment. The approach distance for an unqualified operator is 10 feet. That's a newer OSHA requirement as well, which I know OSHA bases their stuff off of the NFPA and NEC. But if you are not a qualified operator working in or near a dielectric withstand or high pot testing station and the circuit is active and you have exposed conductors, they're not to get within 10 feet of those exposed conductors, and that's an important number to remember. If an auditor were to come through and see you getting closer than that to such a circuit, you can be fined for every single instance of somebody getting within that. So not just one guy happens to make a mistake. If you have 5 different lines and those guys aren't qualified and high pot testers are sitting right there, you can get fined for every single line. Number 4, identify and understand the relationship between electrical hazards and possible injury. And we've kind of already covered this. The effects of electrical current on the human body, the different paths it can take through the body. It's good to know that stuff. If you're going to be dealing with a dangerous situation, it's good to know about the danger. If I'm training dogs, it's probably a good idea to know what a dog can do to you should he happen to bite you. It's kind of common sense there. Number 5, know the safety features of the equipment and know how to use them. Every piece of equipment will have some type of safety feature on it, hopefully if it's manufactured well. For example, our high pot testers have our patented smart GFI circuit, which is able to recognize if there is stray current flowing to ground. Because what the unit then assumes, if there's stray current flowing to ground and it's not coming back through the return, somebody must be touching the device under test, and I'm going to shut off immediately. And you can actually, on some of our units, set the threshold. On some units, it's a default 400 microamps, and it'll shut off if it senses any stray current beyond that. We have an interlock built into ours as well. Most high pot testers have them, an interlock, which basically means if that interlock is not in place, the unit will not output voltage. And we'll get more into detail on that in a little bit, talking about the interlock. Automatic discharge circuits. Our units have auto discharge circuits built into every one, which means once the test is done, it's going to discharge the device under test so that once the test is done, somebody walks up and touches the unit, they're not going to get hit because it was charged up. But there's a couple points to remember about discharging that I will get into in a moment here. Determine if PPE is necessary. Remember that safety approach, or that prohibited approach distance I was talking about, that 2 feet 2 inches? If you guys are going to get within that range, and it's between 750 and 15,000 volts, which if you're running a high pot test, it most likely is in that range, use your PPE, know how it's rated, know how to use it. So the guy they show here, he's wearing high voltage gloves, he's got on safety glasses, and he's wearing his handy-dandy high voltage insulation boots as well, which basically isolates you from ground potential. So not a very attractive path if you have on insulation or isolation boots. Number 7, know the methods of release for victims who are being shocked. Do not touch someone who's being shocked. As you can see in the bottom picture there, it's going to be a bad day. The current will go right through you as well. So the top picture there, what I'm showing is like a fiberglass pole or wooden, something that's an insulating material so that you can get somebody all away from the electrical shock hazard but not get shocked yourself. Another means of releasing somebody could be an emergency stop switch. You see somebody getting hit and there's an e-stop on the system, slap that e-stop as fast as you can because it will cut off power to the system. And then you will be releasing the person from the shock hazard. Understand that a tester is a variable voltage power source. Even though the high pot tester is high voltage, lower current, it's still a variable voltage power source. Contacting a device under test during the test results in a dangerous shock hazard. I think that kind of goes without saying with everything we've been talking about here. Know the importance of discharging your DUT. There must be a complete path for an instrument discharge. Be wary all leads are connected, and that's something I just mentioned. Yes, all of our testers will automatically discharge, but only if the leads are attached. If somebody knocks off the return lead in the middle of a test, all you're doing is charging that thing up. And if somebody goes and touches it, they are going to get hit. The unit can't discharge if there isn't a complete path. I don't care how good the technology is, it's just a physics thing. So you got to always make sure that your leads are properly attached. There's things you can do on the instrument to make sure that's the case. You know, making sure you set a low limit parameter, for example, as a leakage limit. You know, if you know that your product, when you high pot test it, gives you about 3 milliamps of leakage current, go ahead and set your low limit for, let's just say, 1 milliamp. So if it goes below 1 milliamp, the test fails, letting you know, hey, I just got a low limit failure. Maybe my leads aren't attached properly. That saved a lot of headaches on a lot of customer sites that I've seen is setting such low limits. And then, of course, number 10, each step in a work plan must be executed. Do not take shortcuts. I know that sounds kind of common sense, but I've seen a lot of production lines, and you'd be amazed when somebody wants to try to hit quota for a production line, the steps they will take to try to get around certain work plans. And that's when we've seen people get hit by the high pot testers as well. You know, it's never been a case where it was fatal, fortunately. That's never happened, but somebody gets whacked, and it's not a good feeling, and it scares them. It startles you. It makes you kind of reconsider the equipment that you're using and the kind of situation that you're in. So keep these in mind. If you're people and the operators and you guys know all these things and you're solid with all those, you should be in really good shape. I would consider you to be a qualified test operator if you knew all this stuff. So on top of being very knowledgeable, which, by the way, those 10 things, that's your best defense against a shock hazard. Being wary, being smart about it. If you're qualified, that is your absolute best defense against electrical shock hazards. But we can also build safeguards into a station. You can put enclosures in. That's designed to remove a shock hazard. If you can't touch what's being tested, you can't get shocked. Cabling and insulation, like test probes, for example. Personal protective equipment, like we explained in the other slide where it showed the glasses, the gloves, and the boots. And then just being aware of your nearby hazards. So let's look at some examples here, which kind of lay out some nice stations for methods of safety testing. Now what we have here is a test station with positive protection. When I say positive protection, what I mean is the operator cannot touch the exposed energized circuit while the test is in progress. So why is this a station with positive protection? Well, that's because of what's labeled A right there. Now A is a safety enclosure, and you'll see inside of that, what in this case looks like a plexiglass box, is what we're testing. B is the high pot tester itself, and C is the test operator. So what we have here is a test operator working with the high pot equipment, and the DUT, or the device under test, and the test leads from the high pot tester are all enclosed in that enclosure. This is positive protection, and what we've done here, the door of that enclosure is built into our interlock. And what that means is we have a magnetic switch on the door of the interlock. So if that door opens while the test is running, the interlock is broken and the high pot tester immediately stops outputting voltage. So basically you can't run that test if that door is open. That's what we call positive protection. So you can see, as I mentioned, A is the enclosure, B is the high pot tester, C is the operator, D is an insulation mat. It's kind of the same concept as boots. It isolates you from a ground potential. E is what we call a signal tower light. And I've seen these on a lot of stations as well. So basically that red light goes on when the test is running. And when it's idle or the station's not in use, the green light's on. Sometimes I see yellow as an intermediate, but mostly it's just red-green. You'll notice there that I also have the 10-foot number there, which is I'll get to in a second. F, we have an emergency stop switch for the high pot testing station, so that if something goes wrong, somebody can hit that E-stop and shut down the station. G is a high voltage sign, which I recommend if you have a high pot testing station, there's others that come in the immediate area, get one of these signs. It's just good to have. It just lets people know, hey, there's high voltage in this area, don't cross this boundary, especially if you're not qualified to work in here. And then H, I'm sorry, is just the DUT itself and the enclosure hood. And then I is, oh no, I'm sorry, my apologies. H is the workbench. That's what that I meant to say there. A non-conductive workbench. You do not want to be testing on a metal table. You would think that goes without saying. You'd be surprised how many of those I've seen. Do not test on a metal table. Just not a good practice. That one's just wood. The ones that we have in our labs are your standard work test benches, which are all made out of wood as well, some kind of non-conductive material. And then I there is what that's showing you is that those are other operators working at other stations. They are not qualified to work with that test equipment, so we have the 10-foot number there. Now, something I should note, the 10-foot rule comes into place with exposed conductors. Technically, those guys could be closer than 10 feet because you're using an enclosure door there, so it's not an exposed conductor. So I just wanted to make that point very clear. If you do have a DUT enclosure door over what you're testing, you can have other operations going on closer than 10 feet. You won't get in trouble for that because the conductor is not exposed. So I just wanted to make that real clear because it's not directly clear from the picture. So now let's look at a station that does not have positive protection. And this can happen. You know, you might be testing something that's far too large to put inside of a full enclosure. It's just not practical with the way the line is set up. It's an infrequently used station. It's a lab. Whatever the case might be, there are a lot of scenarios where it's realized that you just can't have an enclosure covering everything. So what we have here is a station that does not protect the user. It has no positive protection. But there's still things you can do. So as you can see, A is labeled the device under test. Looks like a big dryer or washer or something. B is the high pot tester. C, once again, is the operator. D is the insulation mat. E is, again, a signal light. F, we have our emergency stop switches. G, we have our danger high voltage signs to keep people out. And in this particular case, you can see we also have a big high voltage sign on the door to that screened in area. And that's the other important thing to point out here. You'll notice the screened in area is guarding from anybody getting in there if they're not a qualified operator. So that's a really smart thing to do. It doesn't have to be a full-on fence or anything like that, but at least roped off, which I've seen. You know, you've seen those yellow chains with pylons that they have an area roped off, or maybe even tape on the floor, like danger, high voltage tape on the ground, you know, marking off a 10-foot space so that unqualified people can't get within there. Now this one's especially important. The 10-foot rule would definitely apply here because that is an exposed conductor. If you're running a high pot test on that thing, it's exposed. You can't have unqualified people getting within 10 feet of that, okay? So just a couple different scenarios I wanted to run over to make sure that that is understood. And we have another poll question for you guys with regards to what are you using on your workstation to protect people? What kind of safeguards do you have built in? For this poll question, feel free to click as many as you want. Feel free to click as many as you guys are actually using, so I'll give you another 30 to 40 seconds to answer that.
Hey, Nick. So for the results for this one, we had 62% are using warning signs, 44% are using an insulation mat, 16% signal light, 44% DUT enclosure, and 22% palm switches. I'll hand over the presentation back to you.
Okay. 44. Those are good numbers. I'm proud of you guys. That's excellent to hear that almost half of you are using some really good ways to protect operators. In my personal opinion, if you really want to eliminate a lot of doubt about a station, the DUT enclosure is the best way to go because you've just eliminated an exposed conductor. That is the absolute best way to go from guarding people because it immediately provides positive protection. But again, we understand not everybody can have an enclosure for whatever reason. But we've talked about a lot of different ways that you can protect your operators. So excellent. Those were some good numbers to hear. The palm switches was interesting too. That's another really good way. If you cannot have a enclosure, that's another really good way to go. I just wanted to show you guys an example. This is something a customer was nice enough to allow us to photograph. Nice little station here. You can see our test equipment is on the shelves up above the PC, and the PC is running our software. A little bit of an older setup. That's one of our previous generation units, but obviously the same rules would still apply. So you can see they have a full plexiglass enclosure to test their product. So there are no exposed conductors there. And they yet still have danger high voltage tape there, which is excellent. They kind of took an extra precaution. So I just wanted to show you guys, I showed you some diagrams that we made up, but I wanted to show you an actual setup which is very applicable here. So aside from what we'd already talked about, here's some additional methods for operator safety. And clearly from the poll, some of you are already aware of this. Dual remote POM switches. Why is this safe? Well, because it doesn't allow the operator to touch the DUT. The way that we have an option on some of our instruments, it's the dual remote POM option. You have to simultaneously activate the buttons, or they have to be activated within 0.5 seconds of each other, and your hands have to remain on the buttons the entire time that you're testing. If one hand comes up of either button, the test will stop. And that's the way you want it, because then the operator cannot have a free hand. This is especially helpful if you cannot have a DUT enclosure, because the operator can't touch it. If he or she has to have their hands on the buttons, they can't touch the DUT. So that's kind of the idea there. Another thing you can do is the lights, as I mentioned, illuminates red when a test is active, and it's mounted in plain sight for the entire work area. And then, of course, an insulation mat. It isolates the user from a ground potential. Simply put those on the ground right by the testing station, and it will greatly mitigate your shock hazard. Just something I wanted you guys to keep in mind here before we move forward. I do have a video demonstration I wanted to show you with two different ways of testing. So I wanted to show you some live examples before we end it. If you visit our website, if you go to our accessories page, we actually do now offer various means of protection. We offer insulation mats. We offer high voltage warning signs. We also offer signal lights, the red-green signal lights. In the near future, we will also be offering dual remote POM switches, emergency stop buttons, and we also offer DUT enclosures. So we have various means of helping you protect your operator, and we also offer them as packages. So you can get multiples in one and get a good discount on something like that. So something to keep in mind. Just visit our website, or you can talk to one of us directly. So that being said, let's get into a couple video demonstrations here. So first I'm going to show you a workstation with positive protection. So what I'm showing you there, you can see I have a signal light that's illuminated red because I'm ready to go with this test. I have a DUT enclosure, so if I open the door, you can see my test device in there, and I have an Omnia unit. And you have to forgive me, I'm not a professional photographer. So that enclosure door is actually wired directly to the Omnia. I mentioned the enclosure and how it's wired to our interlock. So I'll start my test, and I'm going to then open the door. So as soon as I open the door, you see it says interlock is open, the test stops. That's the idea. We don't want it to go any farther than that. So if I leave the door closed, obviously the test is going to run through to completion, and you're good to go. So just a quick example there. And then here's a test station with no operator protection, but you'll see I have dual remote POM switches. Before I start this video, you'll see I'm pointing at the POM switches right there. I kind of have these set up funny, and I'm going to be standing off to the side because I wanted you guys to see me actually activate the switches while I'm doing this. So I'm kind of at a funny angle in this particular video. Again, I am not a professional cameraman or anything like that, but you can see on the top there we have a red light because we're ready to go with this test. On the right-hand side, you'll see we're testing a rather large device under test, so I couldn't use an enclosure, but I wanted to show you guys the use of the dual remote POM switches, which we have here. There's our DUT. So if I push one button and I wait and push the other one, you notice nothing happens because I waited more than 0.5 seconds. If I try to test, my unit doesn't let me test because it's waiting for me to activate the test through the buttons. It's basically saying, nope, you can't use this test button, got to use the dual POM switches. So now I'll put them at the same time, then they go. But if I lift my hand off of one, you'll notice, you can kind of blurry, but you can see the abort message on the screen because I lifted one of my hands. I have to keep them on the whole time. So now I'll reset and put them both at the same time and hold them down. And then we were able to pass. So just another example of how you can protect yourself with these very simple methods. All right, so almost finished up here. Thanks for bearing with me, everybody. Training resources. OSHA, 29 CFR, Part 1910.332, Subpart S, and it defines training requirements for anyone exposed to voltages in excess of 50 volts. Type that exactly as I have it there on Google. You can go to the OSHA website. It's all free information. NFPA 70E, standard for electrical safety in the workplace. So that one you would have to pay for, but it's very good. There's a good chance if you work at a large facility, you guys already have this in-house. And then one of my favorites, now it's an EN, a European norm standard, so it doesn't particularly apply here in the United States, but it is an excellent standard for considering safety stuff for an electrical workstation and the high pot equipment itself. I highly recommend that you get the standard and you look over it. You do have to buy it. I think it's right around 100, 150 bucks. Nice thing is it's only about 20 pages long. It's not one of those standards that's 300 pages and goes over all these different things. It's very to the point. It's straightforward. I think it's an excellent standard. It's written very well, and it explains what you need to do in order to have a safe station. Also, as always, go to our website. You'll notice a tab on our website that says training resources. We have white papers. We have our webinar archive. All this information is free for you guys to access. Again, if you'd like a copy of the presentation, let Jim know. Don't forget to check out our website for resources and follow us on YouTube, LinkedIn, and Twitter. We have a lot of updates, a lot of information. On YouTube, we have a lot of videos that show examples of testing using our instruments, all kinds of stuff. And then on LinkedIn and Twitter, we always have updates on new product lines, new safety features, stuff like this webinar. So follow us on there as well. Again, I really appreciate everybody attending today. Thank you for taking time out of your schedule. We hope you find this information useful, so please provide feedback. And now I will leave the floor open to questions for the next few minutes or so. But thanks again, and we'll see you in November for our next webinar. All right, looks like not too many questions at the moment. If you think of something later, email us at info@asresearch.com. You can contact us directly, and we'd be happy to discuss. Once again, thank you, and have a good day.